Right, so our focus today is circle geometry, and there are keywords that you need to be au fait with so that you can do a link to the theorem. So I'm going to do a walkthrough through the theorems before we actually get into the past paper questions. I've also uploaded a document that has the proofs for the theorems. There are 4 proofs that are uploaded via video. 1 must come out. All right, out of the 4, 1 must come out. So go to those videos and make sure that you learn how to prove the theorems, and that gives you 6 marks in the paper, plus a couple statements. You end up with about 6 to 8 marks. All right, we look at the first theorem, theorem 1. Now, there's no such thing as theorem 1, 2. I'm just giving it a number just to keep track. All right, so we have theorem 1, and the theorem states that the angle at the center subtended, or the angle subtended at the center of a circle is twice the angle subtended at the circumference. And you know this as angle at the center. So if we look at this, very important, all the theorem is telling us that when you have an angle at the center, that angle will be twice the angle at the circumference. So we see these 2 points in the bottom, they produce an angle at the center. And from the same 2 points, it produces an angle at the circumference. So that's our first theorem. And if you look at the slide, you see your 2x, your x. So you can see a relationship across 2x, x. So we have the theorem. Now, this is quite an unusual one. People don't pick this up. But from these 2 points that we're looking at, we have an angle at the center, 2x. So from these 2 points, we have an angle at the circumference, x. So that's a good way to, I want you to point out or make a note of this diagram, because lots of grade 11s miss this one. All right, it's easy for them to see the first scenario. And then if we go on, I just want to look at this case. And if you notice right here, we have an angle at the center, and it's a straight line. So that's a straight angle. So that gives us actually 180 degrees. So if this is 180, it means we have an angle which is x, and half of 180 is 90. And that's also the theorem that we talk about is angle in the circumference, which we'll come to just now. So I'm making a note, watch for this one a little later. So that's our first theorem. Angle at the center is equal to twice angle at the circumference. And we can apply it very quickly. If we are given this to be 84, so we have 2 choices for x. Some are going to tell us 42, and some of us are going to think it's 168. So you got to remember that at the center, if you look at a city at the center, we have more people at the center, okay, compared to outlying areas. So your center will always be bigger. So your center is double the circumference. So x has to be smaller than the center, which will give us 42 degrees. And looking at number 2, in that scenario, we have the angle at the center is y. The angle of the circumference is 35. So we're going to double 35, and that will give us 70 degrees. So these are very simple applications on angle at the center. So let's move on to another theorem. So the second theorem we want to look at is the angle in the semicircle is a right angle. And a right angle means it's equal to 90 degrees. So there's a diameter, and we know diameter cuts a circle into 2 parts, which we call a semicircle or half a circle. So from our diameter, so we have from these 2 points, the ends of the diameter, we have an angle, an angle, and an angle. And all those angles will be 90 degrees. So there's our theorem that states the angle in a semicircle is a right angle. So what I want you to do is just to try and visualize this. So when we go to past papers, you'll be able to see this happening in the past papers. And we don't have to prove this theorem. It's just a special case of the angle in the center. Remember what we said, if the angle in the center is 180, then the angle at the circumference has to be half that, which is 90. And we look at a question, which I think we're going to come to the question a little later, or maybe we should just quickly ponder over it. So if we look at this question that I have in the side, and if this blue line is the angle at the center, sorry, if the blue line is the diameter, because O is the center, so immediately we can conclude that angle A is 90. And we can also conclude that angle D is 90 and angle B is 90 using the diameter. So very first question, to find angle A, it's 90, reason angle in a semicircle. Angle B is also 90. We're looking at, from the diameter, we're producing an angle in the circumference. Notice that this point here has to touch the circumference of the circle. It can't be a random point inside the circle for us to apply the theorem. And if we're trying to find C, this is a triangle, so we can use some angles of a triangle. 180 minus 90 is 90, 90 minus 70 is 20 degrees. So we get our C. And we know D, angle in a semicircle again, has to be 90 degrees. And then to find angle E, we're going to use some angles of a triangle. We have a triangle, some angles of a triangle equal to 180. So it's a very simple question how we apply the angle in the semicircle. Going on to another theorem you've studied. Angles subtended by an arc or chord in the same segment are equal. Now that's the entire statement. You know this as angles in the same segment. And if we quickly look at that, looks like a bow tie. Some people see it as a butterfly. And from these 2 points in the bottom, we can see we have an angle being produced, another angle being produced, and an angle being produced. And all those angles are equal to x. And that is the theorem we're using, angles in the same segment are equal. Looking at another case of the theorem. Some people call this the bow tie theorem. Don't ever say that in your paper. We will not accept bow tie. It may look like a bow tie, but the reason we give this is angles in the same segment. And on the other side as well, we have y and y, if we look at it from the opposite direction. So a very simple application. If we're trying to solve for x and y, and we can see they're coming from the 2 points. From these 2 points in the bottom, we have an angle produced at 38. Therefore, x is 38 and y is 38 because they're all being formed from the same chord. And if we look at the other diagram, we're trying to find x. X should be equal to, coming from the chord that I drew in red, we have an angle called x, and from the same chord, we have an angle called 30 degrees. Therefore, x has to be 30 degrees. And looking from the other direction, we can get y to be equal to 40 degrees. So that's a simple case of angles in the same segment. Okay, we're going to move on to another theorem that you've done. So this theorem, you call it the chord theorem, some of you. A line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. So what is given? We have a center, and we see that B is the midpoint of AC, because AB is equal to BC. So the theorem states if it's drawn from the center to the midpoint, that means that the 2 angles at B will be 90 degrees each. And if we actually put that down, in other words, our conclusion on this theorem here would be that angle is 90 and that angle is 90. Let's call it B1 and B2. So we can say B1 and B2 is equal to 90 degrees. Now, lots of grade 11 struggles for the reason for this theorem. So I would say, what do you see? We see a line from the center to the midpoint That's what we're actually seeing. Our conclusion is B1 is equal to B2 because of the theorem. And then if we look at the converse to this, okay, we're not going to prove that. If we look at the converse to that, we see that the theorem states that a line from the center perpendicular to the chord. So now we can conclude that B is the midpoint. In other words, AB is equal to BC. So those are our two chord theorems. One is line from the center to midpoint, and this one is line from the center perpendicular to a chord. So if we go on now to the next theorem, so let's look at an application of the chord theorems. So if you look at this case here, if O is the center, immediately when O is the center, we know OS has to be equal to OT, radii or radius. And what you'll notice here, if your line is coming from the center perpendicular, immediately your chord theorem says that ST is bisected, which means that has to be 4 and 4. And in a case like this, what we're going to use Pythagoras. So you must be able to see Pythagoras to find OS, which is your radius. And if we do that, using Pythagoras, we can say it's equal to 5, because OS squared is equal to 4 squared plus 3 squared, giving us 25, and the square root of 25 is 5. Okay, there's another case. If O is the center of the circle, now they're telling us that ST is equal to TU. That's the given information. And now our conclusion would be, surely OT is now perpendicular. So that is given to be equal. We can conclude that that is perpendicular. We'll talk about reasons later when we come into the past paper questions. And immediately, we know that angle OTU, you can call it T1 and T2 to reference it, to make it easier, is 90. We're not going to accept the chord theorem, so I'll come to reasons later. Just to let you know, in this case, we should have said line from the center perpendicular to the chord. That will be our reason. Line from center perpendicular to a chord. And then we can find that using some angles of a triangle, and the triangle I'm highlighting is in red, we can use some angles of a triangle, take our 180 minus 90 minus 22 is 68. Now we know if that angle is 68, surely OS is equal to OU. And if OS is equal to OU, we have radius. Therefore, we see an isosceles triangle. And therefore, X has to be equal to 68. And we can't use isosceles triangle. We're going to use angles opposite equal sides. Okay, so I deliberately put the isosceles to show you we're not accepting that. It has to be angles opposite equal sides. I know some of you would have told me we could have concluded that this side is 90, all right, and then work it out from the other triangle. Moving on to the next theorem, the angle between a tangent and a radius is 90. This is very important for analytical geometry as well. So if you got your radius, at the point of contact, it will be 90 degrees. So that's your tangent that is perpendicular to your radius, or your radius perpendicular to a tangent. Very important theorem for us to use. And if we look at that from the other side, radius perpendicular to tangent. So I just want you guys to try and visualize this. before we actually get into the past paper questions.